Chapter 12, Experiments and Observational Studies. In observational studies, researchers do not assign choices, they observe them. In a retrospective study, subjects are selected and then their previous conditions or behaviors are determined. They're not based on random samples. They focus on estimating the difference between groups or associations between variables. They're based on historical records that can have errors. A prospective study, no treatments are deliberately applied, therefore it is not an experiment. The subjects are followed to observe future outcomes. They focus on estimating differences among groups during the course of the study. Experiments require random assignment of subjects to treatments. The designed experiment is required to establish cause and effect. They study the relationship between two or more variables, and they require at least one explanatory variable, known as the factor, and the explanatory variable is manipulated. They require at least one response variable, known as the response, and the response is measured. Individuals on whom or which we experiment are known as subjects, participants, or experimental units. The levels are specific values that the experimenter chooses for a factor, and the treatment is the combination of specific levels from all factors that an experimental unit receives. Let's look at an example of an experiment. Does the amount of sleep and exercise you get affect your performance? So we have two factors, sleep and exercise. Sleep has 3 levels, 4, 6, or 8 hours, and exercise has 2 levels, 0 or 30 minutes on the treadmill. So the 3 sleep levels and the 2 exercise levels yield us a total of 6 treatment levels. Now the table below lists them out. So you can sleep for 4 hours with 0 minutes of exercise, sleep 6 hours with 0 minutes of exercise, sleep 8 hours with 0 minutes of exercise, or sleep 4 hours with 30 minutes of exercise, sleep 6 hours with 30 minutes of exercise, and sleep 8 hours with 30 minutes of exercise. So there are 4 principles of experimental design. The first is control. So control the sources of variation other than the factors we are testing by making conditions as similar as possible for all treatment groups. The second is to randomize. Allows us to equalize the effects of unknown or uncontrollable sources of variation. Assigning experimental units to treatments at random allows us to draw conclusions from an experiment. So number 3, replicate. We must be able to repeat or replicate the results. So we want to apply the treatments to a number of subjects. An outcome of an experiment on a single subject is an anecdote. It's not data. We also want to repeat the experiment on a different population of experimental units. Number 4 is to block. This is an important compromise between randomization and control. So we want to group similar individuals together and then randomize treatment assignments within each block. So let's look at an example with blocking. So we have the same question here. Does the amount of sleep and exercise you get affect your performance? We have the same 2 factors, and we have the same levels, and we have the same 6 treatment levels. What we've done differently here is we've blocked on male and female. So we're going to have one block is all males, and we're going to randomize assignment within those treatment levels for males. We have another block of females, and we're going to randomize treatment assignment within that block of females. So what makes a difference statistically significant? Well, the observed difference is bigger than just from the randomization alone, and the observed differences are attributed to the treatments. An outcome is statistically significant if the probability that it happened just by chance is so low that we are convinced there must be another explanation. Sample surveys try to estimate population parameters, so the sample needs to be as representative of the population as possible. Experiments try to assess the effects of treatments, so experimental units are not usually drawn from the population at random. So a control treatment is a baseline measurement, and a control group is the experimental units to whom the control treatment is applied. In experiments, we can also do what's called blinding. Now, in an experiment, there are two classes of individuals that can affect the outcome of an experiment. The first, those who could influence the results. They may be the subjects, the treatment administrators, or the technicians. The other group, those who evaluate the results, could be judges, treating physicians, etc. So we can do what's called a single blind experiment, where all of the individuals in either class are blinded, or we can do what's called a double blind experiment, where everyone in both classes is blinded. Now, you may have heard the term placebo, and the placebo is a fake treatment that looks just like the treatment being tested. So it could be something like a sugar pill or colored water or something like that. Now, the placebo effect is when experimental units show a response even when administered a placebo. So let's say, for example, you are testing a painkiller, and you have a group that gets a specific dosage, and then you have another group that gets a different dosage, and you have a third group that you give a placebo to. Now, let's say you have members of that third group who receive the placebo that have a response to the painkiller. Okay, they say, yes, my pain level improved. Okay, that would be the placebo effect. So the fake treatment that you gave to that group is the placebo, and the placebo effect are people in that group saying, yes, they had a reduction in pain. We use blocking when groups of experimental units are similar. By blocking, we isolate the variability attributable to the differences between blocks. It allows us to see the differences caused by the treatments. In a randomized block design, experimental units are randomly assigned treatments only within the blocks. Blocking in experiments is based on the same idea as stratifying in sampling. So remember, in stratifying, we had homogeneous groups in each strata. So if we think about the example that we gave earlier in this chapter on the sleep and exercise experiment, we blocked off of males and females. So the males only have males in them, the females only have females in them. So that is a homogeneous group, or two homogeneous groups, males and females. Now, you remember the term a lurking variable. We've talked about that a couple times so far, but here's a new term, confounding. Okay? So when the levels of one factor are associated with the levels of another factor, the two factors are confounded with one another. A confounding variable is associated in a non-causal way with a factor and affects the response. Because of the confounding, we cannot tell whether any effect we see was caused by our factor or by the confounding variable, or both working together. Now remember, a lurking variable is one that's associated with both x and y that makes it appear that x may be causing y. Let's look at an example of confounding. So does drinking 8 glasses of water a day reduce the chances of catching a cold? Well, volunteers are randomly assigned to one of two groups. Group 1, drink 8 glasses of water per day. That's our treatment group. Group 2, drink water as you normally do. That's our control group. So the results show Group 1 gets significantly less colds than the control group. Does this mean that drinking 8 glasses of water per day results in less colds? Well, our confounding factor, drinking more water leads to more bathroom trips and therefore more hand washing. More hand washing may be the actual cause of fewer colds.